Okay, so in this second video, we're going to continue talking about continuous functions, but we're actually going to look at types of discontinuities. I have 4 types of discontinuities here that you're going to encounter. The first one is called a gap. That's sometimes called removable. Graphically, this is what it looks like, and usually what happens is that you get a 0 over 0. You do not have to have a point. It could easily just be a gap, and you identify it again with a 0 over 0. The second one is a jump. Here's an example of a classic jump, and usually you achieve that with a piecewise function. The next one is called an infinite or vertical asymptote, and of course you see that represented here. Algebraically, it's usually a non-zero number over 0 that you get. The last type of discontinuity is an oscillation. This one we haven't really seen, and it's not that common. But here's an equation that gives you the oscillation we're talking about. So basically, if you were to graph this on a graphing calculator and zoom in, you would start to see that these lines just kind of go up and down, up and down, up and down, and they're not really approaching any specific number. So the limit would not exist there, making this not continuous. Okay, so we're going to take a look algebraically. We've done these kinds of examples before, but now we're just going to formally analyze them to figure out continuity. I have here the first example. It says determine if the function has discontinuity and state the type. Well, we have 2 restrictions for this for sure. It's gonna be x equal to 4 and x equal to -4. And so we are going to be factoring. So I have the top is just x plus 4. On the bottom, I'm going to have x minus 4 times x plus 4. 4, not 5. And so, of course, you see that the x plus 4 cancels. The moment that cancels, that tells me that the restriction that canceled, that's the -4, that would have made this 0 over 0. That is considered a gap. Okay? Now, if we wanted to find the y value, we'd plug it back to the simplified version, and that would give us the y value. Now, the remaining, if I keep simplifying this, the remaining expression is going to be 1 over x minus 4. So the remaining restriction would be 4, causing this to be a 1 over 0. That's a vertical asymptote. So that means that my vertical asymptote is right here. I'm just going to put the A. And I apologize for how sloppy this is. I do not have my tablet with me, so I have to use the touch screen. And it's not as sharp as a tablet. So we've done this before. You just have to recognize which is a gap, which one isn't, and that's your discontinuities. Okay, let's do another example. With a piecewise function, you just have to check the function is going to be continuous to the left of 0 and to the right, because on the top right here we're talking about a parabola. On the bottom right here we're talking about a line. Both of those are well-behaved functions, no discontinuities. So the only possibility is that they do not connect at 0. So what we do is we simply plug in 0 into each piece. So on the top we're going to get, that's supposed to be squared. 0 squared times 3 minus 7. That is -7. And on the bottom, we're going to get 4. See how these are not equal? Since they are not equal, that tells me that we have a jump. Okay, that's a jump. All right. Again, we've kind of seen these before, so they shouldn't feel too new, kind of like a review. The last one I put here, that one is just, you have to be familiar with the notation. You have that 5x plus 2 is what we're going to use when x is not 0. So if we were graphing that, the line would look something like this, except that at 0, this one would have a gap. Okay? And instead of a point at 2, it would have the point at x squared, so 0 squared is 0. So I'm going to do that. So it actually would look something like this. So of course, this is a discontinuity, and this is what we refer to as a gap, or removable discontinuity. Okay? So that is how you identify different types of discontinuity. The last example we're going to see in this video is one that you will probably see on the AP test set up very similarly. It says, find the value of a so that f of x is continuous at x equals 2. So you have to look at this function that was given to you. It is a piecewise function. And what they are asking you to do is to figure out how to make it continuous at 2. Now, a, which is right here, a is representing a number. It's not a variable technically, it's some constant, and you need to figure out what that constant is. This problem is actually very simple because all you have to do is make sure that the two pieces, the top and the bottom, connect. And the way you do that is you take that's a squared plus 3x, and you're actually going to set it equal to the second piece, which is 5x plus a. Put a little tail on that so I remember that it's a. And so basically we need these two pieces to be equal, but we don't need them to be equal all the time. We just need them to be equal when x is 2. So we're now going to take our expression or equation and we're going to replace x with 2. Okay. And then, and then we're going to simplify. So I will get 2 times 2, that's 4a, plus 6. That's a plus there. And then that will equal 10 plus a. And now it becomes a linear equation. I'm going to subtract a. Let me scroll down a little. That gives me 3a plus 6 equals 10. Subtract 6. That's going to give us 3a equal to, let's see, 4. Divide by 3. So that means that a will equal 4/3. So if a is 4/3, you are guaranteed that that top function is that function is going to connect at 2. So basically, set the two pieces equal to each other, replace the x with the restriction or the point where they're telling you that it's supposed to be equal, and solve for a, and you should be done. All right, hope this video makes sense. Good luck with your assignment, and I hope to see you all very soon.